So one of the uses that we had for concavity when we learned about it in the first year calculus course was we learned that when a function is concave down, well, when a function is concave down, it's like this. When a function is concave up, it looks like this. But one of the things we used for it is that when you use a tangent line to approximate a concave down function, we remember that the tangent line always overestimates a concave down function. Similarly, when we have a concave up section of a function and we use a tangent line to approximate, my tangent line is always underestimating the value of function's concave up. So we just want to keep those things in mind as we move forward into the next problem. So here we go. It's a lot of words. So first, consider the parametrically defined function from the first example in the previous lesson. Right. So back in your notes from a few minutes ago, you had x of t is x is t squared and y is t cubed minus 2t squared plus 5. So first, I want us to find the equation of the tangent line to that curve when t equals 2. And then if that tangent line were used to approximate points in the curve near t equals 2, would the approximations be over or under estimates, and why? Right? So the first thing I would want you guys to do is to find the equation of the tangent line when t equals 2. This should be a pretty simple thing. I just sort of want to make sure we remember how to do it. So recall that we need a point, and we also need a slope. Point should be pretty simple. I'm just going to take my t value and plug it into my original parametric curve. When I use x, my x of 2 will be 2 squared, which is 4. When I do y, my y of 2 will be 2 cubed, which is 8, minus 2 times 2 squared, which is still 8, plus 5. So I'm getting 5 there. That means my point of tangency is 4, 5. Okay. Now to find the slope, for the slope I'm going to need the derivative. I'm going to need dy dx. Unfortunately, we actually found that in the previous video, so if you want, you can go back through your notes and find that. Otherwise, you can just take the derivative quickly. It's not a difficult one. It ends up being 3t squared minus 4t all over 2t. And we want to find this slope. We want to find this dy dx when time is 2. So when time is 2, we're going to end up with 12 minus 8 over 4, which simplifies down to 1. So the equation of my tangent line, y minus 5, equals 1 times x minus 4. And we can leave it in that form, or because that slope is so simple, if we wanted, we could make this y equals x plus 1. Either one of those is fine for your tangent line. The second part of the question was, will this tangent line over or underestimate the values of the function if I'm near 2? And what we need to do is we need to look at concavity. So we need to remember our second derivative. If my memory serves me, the second derivative of this thing was, I think it was 3 over 4t. So now that we have this second derivative, we sort of have to look at, so what's happening near 2? And there's two ways to do this. One of them is the incomplete and easy and kind of cheating way to do it. And this is not the way to do it, but I want to sort of show you guys so you see what you're dealing with here. We could just look at t equals 2 and plug it in. If I evaluate my second derivative of that, I end up with 3/8. And we say, hey, look, the second derivative is positive. Because the second derivative is positive, at 2, the function is concave up there, which means my tangent line will underestimate it. Okay, that works. The issue is that only says that the function is concave up at 2. What if right next to 2 it changed to being concave down? Like, saying, this is sort of a gross statement. Hey, look, I'm always concave up. This function isn't always concave up. The right way to do these problems, like if this shows up on the AP exam, the real way to do this is for us to actually apply our test for concavity to this thing. I know it's been a while since we've seen that, but it's worth reviewing. So remember that the test for concavity identifies intervals where a function is concave up and down. The first step in that process is finding the critical numbers of the second derivative. So I already have this second derivative, I just need to know where that thing is 0 or undefined. Well, the only place it's undefined is at 0, so what I do is I take that value and I set up intervals. Right? Remember, we would have one interval that's going from negative infinity to 0, and then another one that's going from 0 to positive infinity. Then on each one of these intervals, I pick a value and I evaluate the second derivative. Right? So if I evaluate the second derivative for t being, let's say, -1, I'm going to end up getting -3/4, which means my function is concave down here. Right? On the other one, I'll do the same thing. d squared y dx squared evaluated when t is +1. Well, that's going to give me +3/4, and so my function is actually concave up on this whole region. Right? So this is getting us closer to, well, rather it's getting us to a better answer. Rather than just saying, hey, my function is concave up at t = 2, after doing this quick little test for concavity, I can say, hey everybody, my function is actually concave up on the entire interval from 0 to infinity. Right? So that lets us say a lot more about how my tangent line is going to overestimate, or rather underestimate, the function. Right? So the last thing I'm going to do is sort of formally write down the answer for this. So the reasoning or the justification you'd want to provide for something like the AP exam would be to say something like this. Because the curve is concave up on the interval from 0 to infinity, the tangent to the curve at t = 2 will underestimate the value of the function for all values of t on the time interval from 0 to infinity. That's just a lot more solid an answer than just saying, hey, for stuff near 2, it'll underestimate. For this one, we get to give an interval and a whole statement of the thing.